Hey everyone, in today's video we are going to be talking about how to differentiate between the parts of the atom, and then also something that is called isotopes, and then also how to calculate atomic mass for an element. So before we get started, the first thing that we need to do is define the different parts of the atom. So in the atom itself, there are three smaller particles in it, which we call subatomic particles because they're smaller than the actual atom itself. These are protons, neutrons, and electrons. In this diagram, you can see that the protons and the neutrons are in the nucleus here. This is where all the matter is of the atom. And so it's very, very dense. And then the electrons are going to be around the atom at a distance. In this depiction, it is an electron cloud, but later we will define that as electron orbitals, which are general shapes in which we can find these electrons. In the nucleus, you can find the protons and the neutrons. The nucleus itself is the center of an atom. It is small, dense, and tightly packed with matter. It contains protons and neutrons and majority of the atom's mass. And this is just kind of like a random fun fact. So it is so dense with matter that if it were the size of a grape, it would weigh over 9 million tons. That's just because it is so tightly packed with matter. Inside that nucleus, the first subatomic particle is the proton. This one has a positive charge to it, and it has a mass of about 1 AMU. So for subatomic particles, they are so small that we don't use like grams to define their mass because it's too large. So we have a special unit that's called an atomic mass unit, and we abbreviate that by saying AMUs. So protons, again, have about a mass of 1 AMU. The neutron is also located in the nucleus, and it has no charge, and that's where its name comes from. It is neutral, and it also has a mass of about 1 AMU. It's actually slightly more massive than the proton, but they have a very comparable mass. The electrons are found outside of the nucleus in the electron clouds. A lot of times you will see Bohr's model of the atom, which is like rings around a target, and this isn't necessarily the most accurate interpretation of electrons. We actually think of these as more like energy levels. These electrons are negatively charged. They have a mass of about almost 0, and the number of electrons equals the number of protons. So if you have this example here is like for hydrogen. So for hydrogen, there is 1 proton here, which is the +1. You also have 1 negative electron. So in an electrically neutral atom, you have a total charge of 0 for the atom. If you're looking at something like lithium, lithium has 3 protons, so that is 3 plus there. Then you have 3 negative electrons, so that's a charge of 3 minus. Again, if they're electrically neutral, those two should cancel each other out. And so you get a total charge of 0 on the atom. That's what electrically neutral means, again, is if you have a 0 charge in the atom. This chart here is just like a nice summary of those subatomic particles, where they're located, the charges that they have, and their mass. So an atomic number for an element is essentially like that element's social security number. It's a number that is special just for that element, and it defines how many protons are in an atom of that element. So for hydrogen, it has an atomic number of 1, which means that there is only 1 proton. This atomic number is also equal to the number of electrons if it is electrically neutral. So this atomic number is really special to that element. Only if it had a different atomic number, then that means it has a different number of protons and therefore it's a completely different element. No, the atomic number on your periodic table is always the whole number on there. So for hydrogen, it's just 1. For lithium, like we just said, it's 3. Helium, 2, so on and so forth. So all atoms of a particular element have the same number of protons and electrons, but the number of neutrons can be different. And so atoms that are the same element, which means again they have the same number of protons, but they have different number of neutrons, are called isotopes. Isotopes have the same chemical behavior. So all the isotopes of, let's say, carbon are carbon and act all the same when they're bonding with other elements. So isotopes, again, have the same chemical behavior because they interact with other elements in the same way. They have the same atomic number because they have the same number of protons. But since they have a different number of neutrons, they have a different mass number, which means if we added up the protons plus the neutrons in the nucleus, that number would be different because isotopes have different number of neutrons, which means, again, they're just going to affect the weight. The relative abundance in which each isotope occurs is going to be different as well. So what relative abundance means is the percent of time we can find that element. So that, again, is different for each isotope. So this is a way we generally express isotopes. Isotope notation can be expressed in 2 different ways. The first way is just me telling you that the element itself and then the mass number. So for potassium-39, this is an isotope where obviously it is potassium, and this last number here is the mass number, which is the number of protons plus the number of neutrons in the nucleus of one specific atom. Another way we can describe that is with this notation here. And so again, if I gave you potassium-39 and told you to write an isotope notation, you would use the chemical symbol here, the top number, and it's always to the left of the element symbol. The top number is going to be the mass number, which is number of protons plus number of neutrons. And then the bottom number here is going to be the atomic number, which is equal to the number of protons. And this is just a reminder that that atomic number is also equal to the number of electrons if it is an electrically neutral atom. So we can find number of neutrons of this atom by taking our mass number and subtracting the atomic number from it. So if I take 39, subtract 19 from it, then I will get 20 total neutrons for this particular atom. So this atom here, if I had asked you for a number of protons, neutrons, and electrons, we would have 19 protons, because that's the atomic number, 20 neutrons, because I take the mass number minus the atomic number, and then 19 electrons, because this atomic number is equal to the number of protons if it is electrically neutral. So here we have 3 different isotopes of potassium. Now they are isotopes because, again, their mass numbers are different, which means they have different number of neutrons. If you look here, this is the only thing that's changing is number of neutrons. So for potassium-39, there are 20 neutrons. Potassium-40, 21 neutrons. Potassium-41, 22 neutrons. But protons and electrons remain the same, again, as long as this is an electrically neutral atom. They chemically behave the same, and then which means they're going to bond with the same types of atoms in the same type of way. So the only difference here is just their weights. So what an atomic mass unit is, again, it's much smaller than a gram, but we use carbon-12 as our definition here. So an atomic mass unit is 1/12 of the mass of a carbon-12 atom. This carbon-12 atom, again, would have 6 protons, 6 neutrons. 1 AMU is pretty close to being 1 proton or 1 neutron, so you see the exact amounts here. Again, a neutron is slightly more massive than a proton, but if you notice the electron's weight here is very, very small. That's why we say it's almost 0. So mass number, remember we just talked about, is the number of protons plus the number of neutrons in one specific atom. It's as if I had a jar of chlorine and I were to pull one atom out and add up the protons and the neutrons of that one specific atom. That would give me the mass number. Now something very different is called an atomic mass of an element, which is the weighted average of all the isotopes that occur for that element. So what this means is I take into account every kind of isotope that occurs for this element. I'm going to use the rate in which it's occurring in nature. That's going to be called the relative or percent abundance. And then the actual mass number of each isotope. Add them all up together, and that's how I get a weighted average. This is going to be that decimal number that you see on the periodic table. And the reason why it's a decimal number is because it is a weighted average of all the isotopes. So if you're wondering what a weighted average looks like, it is most easily described as like your grade in this class. You know that 70% of your grade right now is your test average. So if you don't do very well in a test, it's going to swing your average pretty drastically because it's 70% of your total grade. Same thing here. If you have the atomic mass of an atom, you have chlorine 35 and chlorine 37. Chlorine 35 occurs 75.78% of the time. That means majority of all the chlorine out there is chlorine 35. And so our average atomic mass is going to be closer to that weight. Chlorine 37 only occurs about 24% of the time. And so again, it's kind of like your formative average. It's not really going to like swing the average very much. So if you have a smaller percent abundance, it just means that it occurs less of the time. Like only 24% of the chlorine out there has a mass number of 37. And so we just need to use that in our calculation. So on the next slide, I'll show you how to do that. So in order to calculate average atomic mass for an element, you're going to use the following equation. So this again is that decimal number on the periodic table. You're going to take the mass of isotope 1. If you're given a decimal here, then that's the better number and the more precise number, so we're going to use that. If not, it's fine, you can just use the whole number. We're going to take the mass of isotope 1 times its relative abundance, which is the percent that it occurs, but just as a decimal. So remember that if you have something like 34%, or let's go back here to this previous slide. If you have a percent here like 75.78, to change that to a decimal, you're going to move this over twice. So by doing that, then you it just puts it in a decimal version. That's what we call relative abundance. Plus the mass of isotope 2 times its relative abundance, which again is a decimal, plus, and then however many isotopes. So it's the same kind of formula for depending on how many isotopes it has. So if we take that previous example of chlorine 35 and chlorine 37, chlorine 35 is occurring 75.78% of the time. Chlorine 37 is occurring 24.22% of the time. So we're going to plug this into our formula to calculate the average atomic mass for chlorine. So in order to calculate the average mass, I take the first mass here, which is 34.969. So I'm going to plug that in, times its relative abundance. So I'm going to take its percent, again, move that decimal place 2 times to the left to get 0.7578 plus, I'm going to take the second mass of that isotope, so this isotope here is 36.966 times 0.2422. So if I just type all this into my calculator, please use parentheses or it's appropriate. So you tell your calculator what to keep together, you will get 35.45. Now the way that you check yourself to make sure you're correct is that this should match the number that is on the periodic table. So if you take a look at your periodic tables that I gave you, you'll notice that the average mass, which is that decimal number again for chlorine, is 35.45 on that periodic table. So again, this is just the process for calculating average atomic mass for an element, and this is what we're working in class this week. Also, it's super important for you to know these vocab words, so things like atomic number, mass number, protons, neutrons, electrons, all those things are very, very important, and they all sound pretty similar, so just make sure you have a very good understanding of what each one is. That's it for today, and I will see you guys tomorrow. Bye.